So we will continue today the solution of problems on chapter 2. Just we will wait 1 minute because some students are still joining the meeting. Okay. So we will solve now the following problem. Water is heated in the economizer of the boiler in a power station from 35 degrees to 165 degrees. The tube wall is at 360 degrees and its diameter is equal to 50 millimeters. Calculate the length of the tube required when the flow speed is 1 meter per second. The mean temperature of the fluid is 100 degrees, where rho is 960 kilogram per meter cube. The viscosity is given to be 2.82 times 10 minus 4 meters square per second. The Prandtl number is equal to 1.74. The conductivity is 0.68, and the specific heat is 4,260. So here, let us do a small figure to understand.
Dr. بس we have a white book. Okay, خلاص مش الحل.
Okay, it's fine now.
Yes.
Okay. So first we will draw a small sketch about what is happening here. So we have, if you want, we have a tube, okay, where water is passing through this tube to be heated. So this is our tube. What we know is that when water is passing through the tube, initially it's entering at a temperature of 35 degrees, and we want it to leave at 165 degrees. So the inlet temperature, Tn, is given. Tn is equal to 35, and T out is equal to 165. And they gave us the geometrical characteristic of the tube. They gave us the diameter. The diameter is 50 millimeter. But what we don't know is what is the required length to achieve the cooling, the heating purpose. Okay, so we want to heat from 35 to 165. This is our purpose. To do this, we should design a tube of length that is high enough to reach this temperature. Okay, we know that the diameter used is 50, as we said. So we have D equals to 50 millimeter, but we don't know what is the length of the tube. So the length of our tube is unknown. We should calculate. And the question is, what should be the length L needed to be able to heat water from 35 degrees to 165 degrees? Knowing that the tube wall temperature is at 360 degrees. So first here, how we should think? What is happening here? What is happening? Why we have heat transfer between what and what?
Between the temperature of the surface and the inner liquid.
Very good. So we have a fluid in motion. We have a fluid in motion inside a tube, and as it is moving, it is absorbing heat due to the high surface temperature. So this type of heat transfer is by which type of heat transfer we have this exchange of heat?
Convection.
It's convection. It's convection because we have a exchange between a surface and a fluid. So as the fluid is passing through the tube, it will be heated by convection from the hot surface. Okay, so we can say that since we are working in steady state conditions, okay, why we are working in steady state conditions, because you can see that when we reach a certain stage, we will have the inlet will always be 35 and the outlet is always 165. So we don't have variation with time. We have a problem with steady state conditions. Whenever you have a problem with steady state condition, you can say that Q, so the heat that is absorbed, okay, you don't have any storage here of heat inside water. You just have Q convection, okay, is equal to, if you want here, I will call it Q sensible, which is the sensible heat that will be absorbed by water in order to increase in temperature from 35 to 165. What do I mean by that I do not have a storage? If I have a storage, this means that with time the temperature will increase at a certain location. Okay, here no, I have steady state conditions. So I always have T inlet 35, T outlet 165. If I have storage, the temperature will increase with time at each location. So here in steady state conditions, the convective heat is transformed to sensible heat. Okay, this is the basic equation that I should start by. Now I will say what is the convective heat and what is the sensible heat in my problem. First, heat by convection can be calculated according to which relation? We know that convective heat is equal to the convective coefficient H, okay, times the area of contact between the solid and the liquid. So I will call it ASL, which is the interface between fluid and my surface. And I have times delta T, okay, times delta T. Now, which delta T I should use here? When I say delta T, it's what? It's T water out minus T water in. This is delta T I want.
No, it's between the liquid and the surface.
Yes.
Very good. So it's the difference in temperature between the liquid and the surface. And since the temperature of my fluid is changing with position, so it's starting at 35 and it's ending at 165, I need to define what is called a mean temperature, because also the convective coefficient H will change with position. But in general, what they do, they give us an average coefficient H. So when they give an average coefficient H, they give us a mean temperature, okay? So if you want here, we will have H to be calculated because we don't know H, times the contact area between surface and liquid, times delta T will be equal T of surface, so it's T wall, minus mean temperature of water, so T water mean. Okay, now let us look what are the information that we know for the convective flux. We know the area. We know, if you want, the expression of the area. Okay, what is the contact area between the fluid and the liquid?
IDL.
Yes, it's the following one. If I want to, so this is the area here. If you want, like this, it's a lateral area. Okay, so I have a circular circumference with along a certain length. Okay, the circular circumference is in length is equal to pi d, and then to have the lateral area of contact, I should multiply by the length L. So I will write that this contact area is pi times d times L. Okay, now d is given, L is not. So I will write my equation function of L, since it's my only unknown. Now until now I don't know what is H, but I will try from the given of the problem to find what is the value of the convective coefficient H. So we will see how to find H now. Okay. T wall is given, it's 360 degrees. So I just have to replace T wall by 360. And T mean of water is also given. T seawater mean is equal to 100. So I will replace it by 100. So now I still need to find what is the expression of H. From here, if you remember, in the course material, we said the importance of dealing with non-dimensional numbers. Okay, so you have like Reynolds, Nusselt, Prandtl. Why we use these numbers? Because we can come up with general empirical relations that can be extrapolated to a general problem too. So, for example, if we perform several experiments on turbulent flow in tubes, okay? So here, for example, you have motion in a tube. This is the first condition. You have motion in a tube. The second condition, you should verify if your flow is turbulent or laminar. Because if your flow is laminar, you have an empirical relation. And if your flow is turbulent, you have a different empirical relation. So the first step to do, they gave you Prandtl number. It's given. Okay? And we have developed in the course that H is related to Nusselt number. Okay? So since H is related to Nusselt and they gave me Prandtl number, I will try to use an empirical formulation that will give me the Nusselt number. Now, in order to know which empirical formula to use, I should ask myself, what is my situation I am working in? First, the first thing I know is that I have a flow in a tube. And we call it internal flow because it's inside, not from outside. Sometimes you have flows from outside. Okay, so you have what we call external flow and we have internal flows. So here we have an internal flow in a tube. Okay. So first I can go to a book or to any, if you want, sometimes we have books having several charts. I should look at the section of internal flows in tubes. Okay. Then the second thing I should ask myself about, so this is the type of flow. First, the type, or if you want, the type of geometry. Okay, because here you have to know the geometry of your here, it's a tube. Okay. You can have a rectangular duct, for example. You can have ducts with a cross-sectional area of a square. So depending on the geometry, you will have a different empirical relation. So first I have a tube, okay? Second, I should look at the type of my flow. So second criteria is the type of my flow. So I should look at the Reynolds number. So I should see if it's laminar or turbulent. And to know if my flow is laminar or turbulent, the non-dimensional number I should look for is the Reynolds number. So I should calculate. The Reynolds number. Okay. So it's RE, called Reynolds number. Okay. And if you look at the given, they gave you all the properties of your fluid. They gave you the density, the viscosity, the conductivity, and the specific heat. All you need. They gave you all you need to do your calculations. So first, from definition, the Reynolds number, okay, of a certain geometry is equal to rho of the fluid times mu, which is the times u, which is the velocity of the fluid, times the characteristic length, they call it LC, the characteristic length of your geometry. Whenever, in general, in case of internal flow, in a tube, in a circular tube, okay, so I will specify in a circular tube, you have that the characteristic length is the diameter. So here in our case, the characteristic length is D. Okay? Over, and we divide by mu, which is the dynamic viscosity of the flow. Okay? you have two types of viscosities: dynamic viscosity, which is mu, and kinematic viscosity, which is the symbol of it is like this. So if you encounter it in a certain problem, okay, we also call it mu, and the difference is just that the dynamic viscosity mu is equal to the kinematic viscosity. So I will call it kinematic viscosity times rho. So if they give you, instead of dynamic viscosity, if in a problem they give you the kinematic viscosity, all you have to do is to multiply it by rho, you get mu. Okay. So here they directly give us mu. This is the symbol of the dynamic. This is the dynamic viscosity, and this is the symbol of the kinematic viscosity. Now, we have everything. We have the density. We have the velocity of the flow. It's 1 meter per second. The characteristic length is the diameter here, which is 50 millimeter. Please don't forget to convert units, okay? So here, all of my terms are in SI units. So I convert millimeter to meter. So it's 10 times 10 to the power minus 3. And for the velocity, it's meter per second. For rho, it's kilogram per meter cube. And for mu, I replace by the values they gave me. It is in meter square per second. So it's 2.82 times 10 minus 4. I have everything. I calculate Reynolds. Now, once I have Reynolds, okay, the following criteria is used. Is Reynolds number, if Reynolds number is smaller than 2,200, okay, then it's a laminar flow. And if it's larger than this value, it is a turbulent flow. And don't worry, you don't have to remember anything. So in a problem, for example, if I decide to give you a duct of rectangular shape, I will give you all the information. I will tell you that for this type, Nusselt is given by the following expression. I will tell you that you consider a flow turbulent from when beginning from this value. So this information will be given to you. All you have to know is to know how to deal with it. Okay. So for any problem, I will give with the problem the information you need to solve. Just you should understand what is Reynolds, what is Prandtl, what is Nusselt, and how to use the relations. Okay. So here I calculated Reynolds. The Reynolds number is very high here. It's much larger than 2,200. So my flow is turbulent. Because my flow is turbulent, I will go to the formula sheet or to the charts I have, and I will select the empirical relation for a turbulent flow in circular tubes. Okay. So this is the empirical relation. It's the one we have seen in the course. And as I told you, in case I give you a different geometry, I should give you the empirical relations. Okay. So this is my empirical relation. It will relate the Nusselt number to the Reynolds and Prandtl number. Prandtl number is already given, and Reynolds number was calculated because they gave me all the characteristics of my fluid needed. So I calculated now Nusselt. Once I have Nusselt, I can deduce the convective coefficient, because as we said, Nusselt is defined as the characteristic length times the convective coefficient over K. And now since I have Nusselt, I will use it to find H convection. So the convective coefficient is simply the Nusselt number times the conductivity over the characteristic length. And also the characteristic length, because we are in the case of the tube, it's the circular tube, it's the diameter. Okay, so I replace, and K is given, I get HC. Once I get HC, I can replace into the convective expression, and I get now my convective flux. I am done with my convective flux. Now I should go back to my initial formula. We said that, what was the initial formula? That Q convection, okay, Q dot, look, when they put dot, they mean the rate. So it's what? When they just put Q, it's in joule. When you have Q dot, it's in watt. Okay. So if you want to Because here I cannot put dot, I will put QD. So it's in watt. Okay, Q dot in watt, it's equal to joule per second. Okay, so we calculated until now the convective flux. Now we have this convective flux will do what? What is the purpose of this convective flux? Is to increase the temperature of our water. So water will take this flux in order to increase its temperature in the form of sensible heat. So it will be equal to Q dot of sensible heat in water, of sensible heat in water. Now, how to calculate the sensible heat in water? What should I do? What is the formula? Who will tell me?
MCP delta T.
It's not M dot, okay? If I do MCP delta T, I get my value in joule. Because I need Q dot, which is the heat flux rate, okay? So it is M dot times CP times delta T. And now what is my delta T? It's different than the previous delta T, okay? Here it's delta T in what? In water. Delta T in water, okay? So here I mean by delta T in water, T out minus T in, okay? So let us replace term by term. How can I calculate M dot? What is M dot?
Rho
M
times
dot,
volume.
yes, M dot is the mass flow rate, okay? The mass flow rate, so let me start by what is M dot? M dot is the mass flow rate, and the unit of the mass flow rate is kilogram per second, okay? But here, what do I know about my flow? I know the speed, so I should try to relate the mass flow rate to the speed. This is why I will write that the mass flow rate is simply what? Is equal to rho times what?
Rho times volume.
Volumetric flow rate. Very good. So first, rho times the volumetric. Just 1 second, because someone is entering. Okay. So it's rho times the volumetric flow rate. And the unit of the volumetric flow rate is meter cube per second. And if I have a flow, to calculate the volumetric flow rate, all I have to do is the cross-sectional area times the velocity. Okay, so I can say it's equal to rho times velocity of the flow, which we called here u. Okay, rho times u times cross-sectional area, AC. So u is flow velocity, and it's in meter per second, okay? While the cross-sectional area here, what is the cross-sectional area here?
Pi d square.
Very good, pi d square. Because what I mean by the cross-sectional area, this is your tube, okay? And the flow is perpendicular, is entering in the tube, and it's perpendicular to the following area. This area corresponds to the circular area, which is pi r square, or pi d square over 4. Okay, so now I can write that the cross-sectional area, I can replace it by pi d square over 4. So AC is in meter square, and here AC is, I can replace it by pi times d square over 4. Now times delta t, times Cp delta t, okay? So times Cp delta t. Now delta t of water is T out minus T in, okay? So it is equal to, I replace by 360 minus 35. So as you can see here, For this term, I know everything for Q sensible. I know T out, I know T in, I know the diameter, I know the specific heat, I know the velocity. So everything is known. Now, once I calculate Q sensible heat, it's equal to Q convection. And in Q convection, what is my only unknown? So if you go back, this is your relation. Okay, this is the relation telling you that Q sensible is equal to Q convection. For Q sensible, you know all the parameters. For Q convection, the only unknown now is L because we got already HC. So replacing in the formula, we can find what should be the length of the tube in order to heat water from this temperature to this. Any question for this problem?
Yes, Doctor Anna, I have a question regarding the Nusselt number.
Yes.
And usually we used to take مثلا نحسب أول شيء Reynolds number to see if it's laminar أما if it's turbulent. Then the second step كنا نشوف نحن إذا fully developed at the entrance, at the exit,
Yes,
نطلع
but look
number.
here, okay, yes, I understand what you are saying. Here, you are working in steady state conditions, okay, and you have the inlet temperature. So here, if you want, you assume that the water flow has already passed through a certain section that will allow you to reach the regime that is fully developed regime.
Okay, but
so you
my
are
question
working
is
in fully developed conditions. In general, they will specify for you in the given. So they will tell you, so we are working in fully developed conditions. Or sometimes if you want, the zone of development of flow is very small compared to the fully developed zones, so that you can neglect its effect. So in general, they should give you this information. But if they don't, you can assume that it's already fully developed flow. Okay.
That's my question is also the Nusselt number that we chose here to take. نحن مش شايفينه ولا مرة previously يعني بكل الاوبشنز اللي كان عليها إذا laminar إذا turbulent إذا inflow developing fully developing ولا مرة شفنا هل equation.
This type of empirical equation. Okay, look, what I want to tell you is that for empirical relations, you can have several empirical relations. Why? Because you know that when you do the empirical relation, you do fitting techniques, okay? And since you are doing experiments, you take several points and you try to find a function that match to the maximum with your results. So this is why sometimes, even for the same type of flow, you have several possibilities of empirical relation. So you can find, if you go to references, you might find several developed empirical relations for the same type. Now, which one to select? Okay, based on research, based on experience, we can know that, for example, this one works better, or here you have, for example, it's a smooth surface. In case you have a certain roughness, Nusselt, the empirical relation will be different.
Okay.
Okay, so even sometimes, yes, it might be new for you because even for the same type of flow, we have several works done. You know that in sometimes, for example, when I studied such courses, they gave us for the same type several possibilities. You can work with this, you can work with this, you can work with this. But based on experience, for example, they say maybe in this range, it's better to work with this empirical relation. And in another range, the following empirical relation is better. So even if it's turbulent, sometimes you can have that a relation is working better in certain zones. Okay, because Reynolds higher than 2200 is, you have a very wide range. So sometimes some empirical relations can work better in certain Reynolds zones than others.
Okay.
Okay. Yes?
I have a question من ناحية الformulas. Yeah, I know there are several formulas, the Nusselt number وهيك. فنحن بالexam when we're solving, will you be giving us which formula the Nusselt number نمشي?
Look, I just talked about this. I am saying that you should understand how to deal with these numbers. But I can give you any type of flow, and I will give you all the information with it. So if I give you, for example, if it's not a circular tube, if I give you a rectangular duct, for example, or a duct of cross section of a square, I will give you all the information. I will tell you that if it's turbulent, this is the formula for Nusselt. If it's laminar, this is the formula. I will give you all the information required. Okay, you don't have to remember anything. You don't have to bring anything with you. I will give you all the information needed to solve a problem. You just should know how to deal with your variable. You should know to write this equation that the convective heat is transformed into sensible heat. You should know this. And you should know that HC, you can get it from Nusselt. Okay, then from your given, you will see that if you are working in turbulent or in laminar regions, and based on that, you select what is the empirical relation needed. So I might give you several relations, and based on your problem, you select the corresponding one.
Okay, this sounds great. Thank you, Doctor.
Welcome. Any other question on this? Okay. So let us move to another problem. Let me check just the chats. Oh, Ibrahim, if we have a phase change of water, of course it will be different. Okay, so if you have change of phase during the convective process, then you will not have to deal with sensible heat. You will deal with latent heat. And in case, so whenever you have a mixture, instead of having the transformation of your convective heat into sensible heat, it will be transformed into latent heat. So if you remember, we did already a problem before. It was the problem of ice and in a cube, and heat was transferred towards the cube by conduction. If you remember, the equation we set in the previous problem was that Q conduction equals to Q latent. So as you can see in these problems, you can see how we can transfer a type of energy to a different type. So you can transfer conduction into latent, you can transfer convection into sensible. Sometimes you can have, if it's not a steady state conditions, you can have first a phase where you have change in phase, then you can have another phase where you have sensible heating. As we have seen in a previous problem also, we have provided heat for a very long period of time. So we changed phase from ice to steam. Okay? So you can have all these types of problems. Okay. Now, we will move to another problem. If this problem will allow us to calculate the solar constant. What is the solar constant? The solar constant is an estimate of the solar power per meter square incident at the equator level. Okay? So let us consider, and you know that the sun is very large compared to the earth. So we can, because the radius of the sun is very big compared to the radius of the earth. So nearly, we can consider that with respect to the sun, the earth is nearly a point. Okay? And we know that the solar radiation emitted by the sun will be received by the earth. The purpose of this problem is to calculate if I don't have the atmosphere, if I don't have anything. Okay, so of course it's an assumption. It's not true because I have the atmosphere, and you will see that the atmosphere will not, a portion will be reflected to the sun. Okay, so not all the solar radiation coming from the sun will cross the atmosphere. A certain part will be reflected, but the part that will be transmitted to the earth will be taken into consideration. Here, in this problem, we assume we don't have anything. So if we don't have the atmosphere, if it will transmit completely the radiation of the sun, what will be the solar power, which is the, if you want, the power per meter square incident at the equator of the earth. So let us consider, since you have nearly, the earth is very small compared to the sun, so it's nearly a point, but at a certain instant, okay, you have that half of the Earth will see the sun and the other half will not. Why? Because here, if you want the rays, so if we do a small sketch, let's say you have emitted rays, they will cross here the Earth. Okay, so this part will be exposed to the sun, the upper part, while the lower part will not be exposed to the solar rays. Okay, so always we consider that the radiation of the sun will be absorbed by, if you want, the upper part only. Okay, and if you from physics, or math, if you want, in math we know that if I have the following, if I have, for example, a semi-sphere, and I have, let's say, a flux from all directions like this. Okay, if I want to compute the total flux received, what I do is the following. Look, if you look at the symmetry, due to the symmetry along x direction, what will happen? So here you have your rays are along different directions, okay, along x and y. But if you do the summation along x, this is x direction, okay? Along x, the components will cancel each other, because as you can see, for each one you have an opposing one. So along x, let's say this component will cancel this one, okay? And here, for example, for this arrow, I can divide it into two parts, one in x and one in y, okay? And here also the same. But as you can see, the x components will always cancel. However, all y components are downward. So you have a property in mass that will say that if I have a flux that is hitting a semicircle, okay, or a semi-sphere, then I can say that the total flux absorbed, if you want, will be equal to the solar, here we call it solar constant. So the solar constant that is in watt per meter square, okay, it's like it's crossing an area of times pi times radius of the Earth square. So we consider, if you want, that it's equivalent to a flux hitting this surface, this one. So if I draw it here, okay, if you look from the top, what you will see, what you will see at the equator level, okay, at the equator level you will see a circle, and this circle has a radius equal to RE. So the cross-sectional area on which we have the solar flux hitting is this one. It's equal to pi times radius of the Earth square. This is why we consider that this is the area that will absorb this flux. Okay, so the total flux that is absorbed by the Earth at a certain instant will be equal to the solar constant times the projected area, which is equal to pi times radius of the Earth square. We will continue this problem in the new session, okay, because this one time is over for this one. I'll send you now a new link.